does that. All the rest of them, they slice through at one spot at any given moment. All right. Remember, fast forward, rewind as needed in this video to get to the problems that you actually need. All right. Okay, check this one out. This is use this graph to actually make true or false statements about each of these. This is a little tricky. It's got some goofiness. This graph represents a function. Yes, it passes the vertical line test. Anywhere I slice through it, it only goes through at one point at any moment in time. So this would be a yes, all right? So true, okay? The domain of this function, x values, is only positive numbers. So the x values go this way. Well, they'll keep going that way, right? This is x values and x values. Remember, the domain is the span this way and this way of all the x values that work. Well, it keeps going forever and ever and ever in the negative direction, so this is false. The range of this function is all real numbers greater than or equal to 1. All right, here's 1. Range is the y values. Yes, it's all y values that are larger than that particular point, or equal to, and so that is true. This function is continuous. Yes, continuous means that it's not individual points, but it's a collection of points connected by a line or a curve. All right, and so this is true, yes. And the next one right here says there are two different inputs that provide an output of 3. So it says, are there two ordered pairs where the output is 3? The y value is 3. Yes, right here and right here, and that's still a function. That's okay, because the x values are unique, but they still have the same output, and that's okay. This particular value right here would be at 1, 3, and this one is at 3, 3 right here. And so this is true, yes. There are two different inputs that provide an output of 3, and that's okay, no big deal. Okay, let's check this next problem. Okay, this is I think our last problem under this section, and then we'll start a new video for the next section. Okay, look at the graph below. Is the domain a discrete function or continuous? This one is called discrete. Look at the points. Point, point, point. It's not flowing continuously through all of the points. Which real-life problem below best fits the data? The depth of a puddle can be a lot of different distances, right? Think about sea level. You can go up in sea level through all of your different distances. 1 foot, 1.2, 1.3, 1 point. You can have a continuous amount, right? And if you ever look at like the stopwatch on, like, say, a phone, like an iPhone I'm thinking of, if you start the clock or the time, it flows continuously through all of its decimals. And so that would be a continuous. So this one's continuous. This one is the weight of your apple. Your weight of an apple doesn't need to be exactly 1. No. Doesn't need to be exactly 2. No. It can actually be a variety of different decimals, right? So this is continuous as well. And so we could write even continuous. So not that one, not that one. This one's continuous. And what about this one over here, the speed? Speed is distance versus time. Time is continuous. You don't just have 1 second go by and then you magically appear at a new distance. No, that doesn't make any sense because this is continuous as well. Continuous means you would graph it with a curve or a line. This one is the cost y to purchase X number of songs. That sort of makes sense because you're going to purchase 1 song, 2 songs, 3 songs, right? Like this. 2 songs, 3 songs, 4 songs, right? Like that. Kind of makes sense. And they're approximately $1 a song or so, it looks like here. And which makes sense because you're not going to buy a half of a song. You're not going to buy 3/4 of a song. You're going to buy 1 song and then 2 songs, all right? And that's kind of the idea behind this situation. Okay, here's our next learning target. I understand the basic characteristics of a linear function. All right, so again, fast forward and rewind this video as needed. Okay, which of the following equations represents a linear function? Select all that apply. Okay, remember that in this situation right here, we want all functions where the x and the y value have not have a degree of 1 is what we call it. They have an exponent of 1. They don't have anything weird happening with them, okay? And so this one has a squared value, and this one has a squared value. So that is not a degree of 1, not an exponent of 1 on the variables. So this would be no, not linear. We would call it nonlinear. The graph of this one actually looks more like a circle, actually, if I can get this to work for me here. It actually looks more like a circle, like that. Okay, this one could actually be written like this. Y equals 3 times 2 is 6x, and 3 times 1 is going to be 3. Well, that's in our generic format of y equals mx plus b, which is, we're going to talk more about that next, in this next section, Unit 6. But this has an exponent of 1 on it, even though it doesn't have 1 on it. It's a normal old y variable, and this is a normal old x variable. And so yes, this is linear, all right? And this one would have a graph that would sort of look like this. It would go through here and kind of rise like that a little bit, something like this, a straight line, all right? This one right here has an x and a y, and there's no exponents on it. So it's actually going to be linear. Nothing weird happening with our x's and y's. Oh, this is weird though. If the exponent is one of our variables, we call this an exponential function. Exponential function, and that is not linear. The graph would look something more like this, all right? That's how the graph would sort of look on that one. Sort of weird. And there's weirdness with our x variable, right? This one doesn't work as well because technically I can rewrite this one using exponent notation. I can actually write it this way. It's actually x to the negative 1. Anytime you have a dividing by x, that doesn't work for us. That's more of a rational function situation. There's some weirdness happening right there. That variable, that creates sort of a weird graph. And I haven't graphed this one for a while, but I think it sort of looks something like something like this. All right, weirdness with the graph, all right? So no, not that one. But yes, this one, this is in that format where the x and the y variable, and this would be linear, and it would actually be something like this, all right? And that would be a straight line, and it is linear, and so just recognizing the format of the equations. Okay, check this out. If the output is my y variable and the input is my x variable, and it says the output of the function is 4 less, here's what it tells me to go do to the input. So it's going to be x minus 4. And it's going to be subtracting 4 on every x value or every input of the function. And so my ultimate equation looks like this. Y equals x minus 4. The output is 4 less than the input, all right? So taking minus 4 from everything. This would turn into negative 1, and this turns into 0, and this turns into 1, and this turns into 2. All right, now I can take that table and I can actually go turn it into a graph. 3 comma, so this is technically 3 comma negative 1, right, like this. And this one is technically 4 comma 0. And this one is technically 5 comma 1. And this one is technically 6 comma 2. And I can go graph those points. I really only need about 3 points in order to graph this. 3 comma negative 1. Over 3, down to negative 1. Boom, drop a point right there. Over to 4, and at 0. So it don't go up or down on this particular point right there. All right. And then this one is over to 5 and up to over 5, up 1. Okay. There is my continuous function of and I'm going to have this as a solid, straight, filled in line, right? Sort of like something like that a little bit. And so when I have this, I wrote you a note on your actual review that says, these don't match this. That's okay. No big deal. They're still x values, all right? So this is my x value and this is my y values. And I want to create my mapping diagram. Mapping would be 0 minus 4. 0 minus 4 turns into negative 4. 1 minus 4 is negative 3. And I draw my arrows straight across on each of these. Okay? Technically, you might want to orient these in the reverse order from least to greatest, or greatest to least is usually, least to greatest. I don't know, this works, great. Okay, and then -2, because it'd be 2 minus 4. 3 minus 4 would be -1, and then draw your arrows. Don't forget to draw your arrows on there as well. That's the idea behind the mapping diagram, is it goes from input to output, domain to the range, all right? Next set of problems that we're going to go over has to do with function notation. So I can correctly use function notation in a context and evaluate the function for inputs and their corresponding outputs. All right, so what is this actually telling me to do? It says, go evaluate this based on the input. And if the input is 2, then it means that the x value is going to equal 2. And if the x value equals 2, then that just means that you take and plug it in. So plug it into this function that's up above. Okay, I'm going to plug it into this spot right there, because that's where the x value was. So this goes into this location. And I put a 2 right there. 7 times 2 is 14, but it'd be a negative, so I go -14 plus 3. And that turns into -11. So my final answer is -11, is evaluate this function based on an input, based on an x value that you're going to evaluate. That's my final answer. Same thing over here, but it's written just a little bit differently. All right, so here it says find the output if you're given the x value. That's not a whole lot different than finding this. I think -3, yeah. F of -3. That's the same thing as this. Same different notation to mean the same thing. So go put that into the equation. So -7, and what goes in there? Well, that goes in there at